Okay, hello and welcome to a brand new unit. We've just finished our unit on volumes and surface areas. Now we're going to turn to some more advanced integration techniques. And today's video is all about integration by parts, which is a very, very fun integration method. A lot of people might hype it up to be challenging and whatnot, and maybe it is, but I think it's a lot of fun, and it really makes you think about how you want to attack the problem. Sometimes it involves some strategy instead of just doing a bunch of trial and error. But before I make it sound better than it actually is, let's start learning about it. So, integration by parts. It can be slightly confusing, but the power of it is undeniable. It is so powerful. We're going to be able to integrate so many new functions that we just weren't able to before. This is going to be an incredible tool. It's going to... What it does is that it integrates the derivative of the product rule, which sounds super confusing, and it kind of is in words, but the meaning of that, it doesn't really matter too much as long as we know how to do it. So we commonly use integration by parts when the integrand is a product of two or more functions. So we've seen some of these integrals in the past. For example, if we were trying to find the integral of 3x e to the x squared dx, this is an integral that, by what we've learned to up to this point, we actually can evaluate this. We just do some u substitution, let u equal x squared, du equals 2x dx. This evaluates to 3x times e to the u times du over 2x. The x's cancel. You can evaluate this further, and it's 3 halves e to the x squared. So this is something we can evaluate using u substitution, and in fact, it is the product of two functions here. You can think of this as the product of 3x and e to the x squared. So integration by parts, it's a similar thing. When we see a product of functions like this, we're prompted to use integration by parts. But if we can use u substitution, then we should just do that. But what if, for example, instead of this integral, it was the integral of 3x e to the x? Now u substitution won't work. We can't let u equal x because we won't be able to cancel anything. If you try letting u equal e to the x or something else, it's not going to work out. So this is an integral we wouldn't be able to solve. For that, we're going to have to use integration by parts. So how does integration by parts work? Well, it has a formula. So if u and v are functions of x and have continuous derivatives, then the integral of the product of u and dv, the derivative of v, that integral is equal to uv minus the integral v du. Okay, we'll try to break this apart a little bit, but it might be a little bit confusing. So in the example we gave from before, 3x e to the x, so this u times dv is going to be this entire thing, 3x e to the x dx. We don't know what u and dv are. That is for us to assign, and then from there we can evaluate the integral. So just like with u substitution, where we assigned a value of u and then solved the problem from there, we have to do the same thing here. Assign a value of u and dv such that its product is this, and then equate the right-hand side. Sometimes we might assign incorrectly, and from there we'll have to reattempt the problem or whatnot, but this is what's going on here. I know it might be confusing that you see a u and a v here. It's just a change of variables. Just like u substitution, we did a change of variables to u. Here we have two variables now. And then on the right-hand side, you see that there is still an integral on the right-hand side. This doesn't completely solve the problem. So you'll also have to evaluate this integral, pray that it's easy to solve, and if it's not, then maybe you're like, oh, gotta try again. So, okay. The key thing to notice here is that even though we use integration by parts when the integrand is the product of two functions, we assume that one of these functions is the derivative of another function, that being dv. So I guess once we do some practice problems, it'll flatten out everything. But yeah, so some tips when we're choosing our values for u and dv. you want to ensure that dv is a function that can be easily integrated, and u is a function whose derivative is usually simpler than u. So why am I saying that? Well, we need to choose a u and a dv from our integrand, and then when we compute the right-hand side, we need to calculate v. From that, we will take the integral of dv to get v. So we want dv to be something that's easy to integrate. And then similarly, within this other integral here, we have a du. So we'll be taking the derivative of u. So we want something that's maybe a little bit simpler to take the derivative. So we want this integral to be simpler. So looking at this here, you can start to formulate what u and dv could be, but I'm not going to tell you that because let's dive into our first problem. It's basically the same exact integral, where we're doing the integral of x times e to the x dx. And we can't solve this using u substitution, as I said before, so we're going to have to use integration by parts. So what we need to do is we need to choose a u and a dv such that their product is equal to x times e to the x dx. And you'll notice that I'm still saying dx when I'm talking about the product of u and dv. That's because this dx is still like part of the integral. And when we're discussing the product of these, this dx will appear on the dv side, because when we're taking the integral of that, we need to have that dx there. So then it's about splitting the x e to the x between the u and the dv. We can let u equal x, we could let u equal e to the x, we could let u equal x e to the x, all sorts of options. So let's try doing u equals e to the x. And then that means dv should be x times dx. So now we see that the product of u and dv does equal x e to the x dx. From here, I like to compute du and v, because I know I need those when I use the formula for integration by parts. So what I can do is take the derivative of, I'll just, so d dx of both sides. So on the left-hand side, we're left with du dx equals, and then the derivative of e to the x is just e to the x. And remember, we want du, so du is going to equal e to the x dx. Further down the road, you'll be able to go from here to here in just one step, where you just take the integral of the right-hand side, or take the derivative of the right-hand side and plop a dx afterwards. But for the sake of demonstration, these are the steps you take to get to du. Now for dv, we want to calculate v. So for that, we need to take the integral of both sides. And the integral of dv is just v. The integral of x is going to be 1/2 x squared. And we don't really need to, we can ignore the constant c. Yeah. The reason is, well, we'll see the reason in just a moment, but for now, let's ignore it. Okay, so now we're going to use our equation where integration by parts tells us the integral of u times dv is equal to uv minus integral v du. So we have, let me underline them, or box them in green. Let me erase these integrals. We have all of the variables that we need, we just have to plug it in. So uv will be e to the x times 1/2 x squared minus the integral, v is 1/2 x squared, times du, e to the x dx. And that's what we're left with. So these are equal. But we still haven't solved it, right? We still have this integral to solve. How are we going to solve this? Well, let's think. Can we use u substitution? Well, let's see. If we let u equal like x squared, that's fine, but we don't really cancel this e to the x at all. If we let u equal e to the x, same problem. If we let u equal x, same problem still. So this integral seems kind of tough to solve. In fact, we might have to use integration by parts again, which doesn't seem fun. Another thing to notice is how this integral is seemingly a bit more complex than the integral we started with, right? Like the e to the x is the same, but this x went to a 1/2 x squared, which just makes things more complicated. So it seems like we're not going down the right path. And sometimes this happens, where you take a moment to realize, hey, this is kind of not where I want to be right now. I think I did something wrong. So when you run into that issue, it's good to restart and choose different values for u and dv. So let's do that. I'm going to erase much of this. Okay. So if letting dv equal x dx didn't work, and letting u equal e to the x didn't work, why don't we just switch them around a little bit? Let's let u equal x and dv equal e to the x. And then just go from there. Still make sure that the product of u and dv equals x e to the x dx, which it does. And then from there we can find du and v. So let's do that. On the left, we'll take the derivative of both sides, and we're left with du dx is equal to the derivative of x is just 1. So that means du is equal to dx. And then on the right-hand side, we're going to take the integral of both sides. The integral of dv is v, and the integral of e to the x dx is just e to the x. So that was pretty simple there. Great. So now let's return to our formula, which I wish I didn't erase it, but I'll just rewrite it. And now let's substitute back in. So u is equal to x, dv is equal to, v is equal to e to the x. We're subtracting the integral of v, which is e to the x, times du, which is dx. And now we're left with an integral that's easy to solve. The integral of e to the x is just e to the x. So this all evaluates to x e to the x minus e to the x, and then we'll tack on the plus c here, right? Because it was an indefinite integral to start with. Great. So now we can just double check to make sure we got the correct answer. And for that, we can take the derivative of what we just obtained, and if the derivative of that equals x e to the x, then we're good. So let's check. D dx of x e to the x minus e to the x plus c, well, that's going to be the derivative of x e to the x minus the derivative of e to the x plus the derivative of c. For the derivative of x e to the x, we'll use the product rule. So that's going to equal x times the derivative of e to the x plus e to the x times the derivative of x. The derivative of e to the x is e to the x, and the derivative of c is just 0. So we can compute this further. Derivative of e to the x is e to the x, plus the derivative of x is just 1, and then we're subtracting an e to the x on the outside. That leaves us with x e to the x as desired. So we did get the correct answer, which is pretty cool. But there you go. That's your first example of integration by parts. And, you know, it's just a perfect example of where we had to restart our entire problem. But look at how much easier this integral was to solve. Would you rather solve this or 1/2 x squared e to the x or whatever it was? Like, nah, this is the way to go. So with things like this, where we're learning new integration techniques, it helps to just grind out a bunch of problems. So that's what we're going to do. We have this integral, the integral of x squared ln of x. We can try use substitution. I'll spoil it for you, it won't work. So we're going to try to do integration by parts. So with that in mind, we can choose our u and dv. So we'll let u equal something, and we'll let dv equal something. And here we can already be a little strategic in how we choose our u and dv. Bearing in mind that we have to take the integral of dv to obtain v, maybe we don't want to put ln of x there. Because do we know the integral of ln of x? I don't, at least not immediately. Actually, I do, but that's okay. Like, it's not a very easy function to integrate. So maybe we want to place that on the u side. So let's give u ln of x, and then maybe give dv x squared dx, something like that. So now you'll notice that like I'm splitting these up, where x squared goes on one side, ln of x goes on the other side. Sometimes you'll see problems where they're not split up. Maybe u equals x squared ln of x. I think there's a problem further down in here where we'll see that, but it's just something to bear in mind. So let's find du. So we'll take the derivative of both sides, and this will give us du dx is equal to the derivative of ln x is 1 over x. So that means du equals 1 over x dx. For finding v, we'll take the integral of both sides. The integral of dv is just v, and the integral of x squared, power rule, 1/3 x cubed. So now we have our variables to work with. I guess I'll draw boxes around them and go from there. Again, remember our formula. The integral of u dv equals uv minus integral v du. Very helpful to memorize that. Just like we had our product rule and quotient rule memorized, this is important to memorize. uv minus integral v du. And now we'll just plug in. So u is equal to ln of x times v, which is 1/3 x cubed, minus the integral of 1/3 x cubed times du, which is 1 over x dx. Cool. So now we can go from here. The integral can simplify a little bit. We see that some x's will cancel out. So on the outside, we have 1/3 ln of x let me make that x cubed over 3. And then we're subtracting away. Let's bring the 1/3 out in front of the integral. X cubed over x is just x squared dx. We can evaluate the integral of x squared pretty easily. That's just power rule. So this is x cubed over 3 ln of x minus 1/3 times 1/3 x cubed. Tack on your plus c and simplify this a bit more as desired. And that should be your answer. As always, you can double check this using the product rule, taking the derivative of it, but I don't feel like doing that right now, so I will leave that for you to do, and maybe we'll do it for some other problems together. But there you go, another problem using integration by parts. As you can start to see, it's pretty similar to things that we're doing. It's just choosing the correct u and dv. Let's do another one. Here we go. This is a good one. The integral of ln of x dx. How are we going to solve this? And maybe you're screaming at me, integration by parts, and like, yeah, you're correct in saying that. But like, if you were to see this for the first time without any priming as to thinking about what integration technique you would use, this is kind of like daunting because there's nothing to work with. It's just ln of x. But indeed, integration by parts is the way to go. U substitution is not going to cut it, and anything else won't work. So let's let u equal something. Let's let dv equal something. So we don't want to put the ln x on the dv part because we know that we don't know how to integrate that. But we know that the dx should go with the dv side, so let's just give dv dx. And u, we said we'll give that ln of x. And sure enough, if we do u times dv, we get ln of x dx, which is our integrand, which is good. So this is a fair allotment of the integrand to u and dv. Now let's just proceed as normal. We're going to find du, we're going to find v. So let's take the derivative of both sides. On the left-hand side, we get du dx. On the right-hand side, the derivative of ln of x is 1 over x. So that means du equals 1 over x dx. Cool. Now, for finding v, we'll take the integral of both sides. the integral of dv is just v, and the integral of dx is just x. So we have v equals x. Pretty simple stuff. I know it looks weird having dv equal dx, but it's fine. Like, there's nothing wrong with it. It's perfectly fine. And from here, we do integration by parts as normal. Let me write out the formula again. Hopefully you're screaming it out with me. This equals uv minus integral v times du. There you go. Hopefully you're starting to memorize it. Now you plug stuff in. U equals ln of x, v is x, minus integral, v is x, times du, which is 1 over x dx. So this simplifies to x ln of x minus the integral of, well, x times 1 over x is just 1, so this would be the integral of dx. We just saw that the integral of dx is x, so this simplifies to x ln of x minus x plus c. Why don't we double check this just to make sure that we're correct? So we'll take the derivative of x ln of x minus x plus c, and we want that to equal ln of x. So this derivative splits apart as follows. For x ln of x, we'll use the product rule. So that tells us that the derivative of x ln of x is equal to x times the derivative of ln of x plus ln of x times the derivative of x. Then the derivative of x is just 1, and the derivative of c is 0. This further simplifies x times derivative of ln of x is 1 over x, plus ln of x times the derivative of x is 1, minus 1. So this is 1 plus ln of x minus 1, which is equal to ln of x, which is exactly what we wanted. So there we go, we finally figured out what the derivative of ln of x. Remember the good old days of derivatives when we were like, oh, the derivative of ln of x is just 1 over x. Well, the integral isn't as pleasant. I do encourage you to maybe memorize this, x ln of x minus x, just because you see ln of x so often, but it's up to you. I feel like I've said ln of x more times today than I have in the past year. Here we go, another question. We have a sine in there. Ooh, how exciting. Can we use u substitution? Am I throwing you for a loop? Is this a trick? Let's think about it. If we were to let u equal something, maybe we would let it be x squared, but then that doesn't cancel anything. If we let it be sine of x, then du equals cosine of x. Nah, and that's not going to work. That means we're probably going to have to use integration by parts. Give a u something, give a v something, or dv something, and proceed from there. So here, maybe it's kind of random how we allocate the integrand to u and dv, but maybe there's a tiny bit of strategy involved. If we remember some of the hints that I gave at the start, it was like choose something for for u whose derivative is simpler, or choose something for dv when taking the integral it gets simpler, something like that. So taking the derivative and the integral of sine of x is basically the same thing. We get like cosine, and the sine really depends on it, like the sine sign. I'm rambling. Anyways, so like we can give that to either one, and then let's give x squared to u, something like that. Let's let u equal x squared, dv equals sine of x, dx. Okay, I'm going to speed through the process of finding du. We'll just do this all at once. So we know we're going to have to take the derivative of both sides and then multiply both sides by dx. So on the left-hand side, we get du dx equals 2x, but then this dx comes on the other side. So we have du equals 2x dx. In the future, if u is easy to take the derivative of, I'll just go directly here because I trust you know how to find your derivatives. With integrals, we can take the integral of both sides. On the left, we have v. On the right, the integral of sine of x is negative cosine of x. Simple as that. And we turn to our formula. Say it with me. The integral of u times dv equals uv minus integral v du. I'm so afraid I'm going to mess this up and everyone's going to laugh at me. But not today. Okay. So this evaluates to what? U is x squared, v is negative cosine of x, minus the integral, v is negative cosine of x, times du, which is 2x dx. We can combine these negative signs into a plus sign. So this is equal to negative x squared cosine of x plus the integral, plus 2 times the integral x cosine of x dx. Okay. So now what? We have to find the integral of this. Well, what's the integral of x cosine of x? Can we use u substitution? No. We can't cancel anything. Does that mean we have to use integration by parts again? Yeah. Sometimes it happens that when you're doing integration by parts, you actually have to do it twice or like multiple times. And sure, that can be annoying, but that's just part of the fun of it all. So let's attack it. I will underline it in red, and then I'll use red pen to solve this integral. So we're now looking to find the integral of x cosine of x dx. And we will let u equal something. We'll let dv equal something. Same as before. Just with a different integral now. So you can choose this however you like. Sticking with the theme of the u and dv from before, we'll give the trig function to dv and give the polynomial term to u. So let's let u equal x and dv equal cosine of x dx. That means du will simply equal dx. Du dx equals 1, du equals dx. And on the right hand side, if you take the integral of both sides, the integral of cosine of x is sine of x. And now we use this handy dandy formula here to say that this equals u is x times v, which is sine of x, minus the integral of v, which is sine of x, times du, which is dx. So this red text is equal to this integral, but this entire term is equal to the integral we're trying to solve for. So let's just write that out fully. The integral x squared sine of x is equal to negative x squared cosine of x plus 2 times the integral x cosine of x dx, which is equal to negative x squared cosine of x plus 2 times x sine of x. Let me change colors actually. X sine of x minus the integral of sine of x dx. So yeah, there's a lot of terms that are generated, so being organized with this is an important skill to have. Now we can simplify this because the integral of sine of x is pretty easy to compute. So we're left with negative x squared cosine of x plus 2x sine of x minus the integral of sine of x is negative cosine of x. So this becomes a plus sign, 2 cosine of x, and then tack on your plus c. That is your answer. No, like, that's a massive answer. There's a lot of terms there just from some seemingly simple integrand. But that's the power of integration by parts. It gets you the correct answer using this method, something that we wouldn't have been able to obtain using u substitution or anything like that. So there we see an example where we have to do integration by parts twice. So if that happens, don't be afraid. Keep on going. Yeah. And maybe you're thinking back to the first example we did, where we had it equal to like, the first time we did it, we had some integral 1/2 x squared times e to the x or whatever. And maybe you can continue going through integration by parts to solve this, because you would need it to solve this. But as you keep on doing that, you'll notice that you're getting further down the wrong track, especially if you're choosing the wrong u and dv's. Anyways, let's proceed with another problem. the integral of arctangent of x. Okay, we don't know the integral of arctangent of x, which is why we're trying to solve for it. So, but we know the derivative of it. Let's just write it off to the side. D dx of arctangent of x. If you are not familiar with the arc notation, this is the same thing as inverse tangent of x. That's equal to 1 over 1 plus x squared. Okay. Well, how are we going to solve this? We don't know the integral directly. We don't know how to do this with u substitution. There's nothing to cancel it with. So that means let's try doing integration by parts. So we need a u, we need a dv. I'm not putting the arctan on the dv side because then I would have to find the integral of it to get v. So that means let me put arctangent of x on the u side and we'll give dv dx. Now we see why I mentioned the derivative of arctangent, because we need to find du. So du is going to be equal to 1 over 1 plus x squared times dx. On the right-hand side, the integral of dv is v, the integral of dx is x. We can use our formula, u times dv equals uv minus integral v times du. And let's substitute. U is arctangent of x, times v, which is x, minus the integral v, which is x, times du, which is 1 over 1 plus x squared times dx. Let's write this a little bit cleaner. X times arctangent of x minus the integral of x over 1 plus x squared dx. And now we're looking at this integral. How are we going to solve it? Integration by parts again? Oh no, that feels annoying. But no, it's not integration by parts this time, it's u substitution. Sometimes you really gotta watch out for it because it'll sneak up on you. And if you can use u substitution over integration by parts, you choose that every day of the week because it's so much easier and much less can go wrong. So what would our u be? Well, we usually like to choose the thing with the higher power, so that would be 1 plus x squared. So let's do that. Du will equal 2x dx. So now we're left with x arctangent of x minus the integral of x divided by u times du over 2x. So that means x arctangent of x minus, let's bring out the 1/2. The x's will cancel. We're left with 1 over u times du. And we know that the integral of 1 over u is ln of u. We'll tack on our plus c, but now we have to substitute what we had for u. So this will be x arctangent of x minus 1/2 ln 1 plus x squared plus c. And that is your answer. So again, not as pretty as the derivative of arctangent of x, but still something to be aware of, and we use integration by parts to get it. It's pretty interesting how this 1 plus x squared is so important in the arctangent world, but yeah, there you go, another example using integration by parts. So still, this, I mentioned before that integration by parts is used when we have the product of functions, and this doesn't really look like the product of two functions, but it is. You can think about this as arctangent of x times 1 dx, something like that, and that works, where we put the 1 on the dv side. That's all that's going on here, so very, very powerful. Let's do another example. Evaluate the following integral, e to the x sine of x. Okay, so, let's see. It's the product of two things. U substitution probably won't work. Let's do some integration by parts. U equals something, dv equals something. So now it's an interesting thing. Taking the derivative of e to the x will just give us e to the x. Same with taking the integral of it. Taking the derivative of sine of x will give us cosine of x. Taking the integral will give us negative cosine of x. It's like basically the same thing no matter what we do. So let's just try something, see if it works, go from there. So let's let u equal sine of x, and we'll let dv equal e to the x. Du will equal cosine of x dx, and v will equal e to the x. Return to our formula, uv minus integral v du, and substitute. U is equal to sine of x, v is equal to e to the x. We subtract the integral of e to the x times cosine of x dx. Okay, now we have to solve this integral, which looks eerily similar to this top integral, but it's what we have to work with. How are we going to solve this? Maybe you're thinking about integration by parts again, and indeed you would be right. So let's try doing it again, and sticking with the theme, we'll give the trig function to u, and we'll give the polynomial, or not the polynomial, the exponential term to dv. So that means du will equal negative sine of x dx, and v will equal e to the x. We'll use integration by parts again, so I'll do it in red text. So the integral of e to the x cosine of x dx is equal to u, which is cosine of x, v times e to the x, minus the integral of v, which is e to the x, du, which is negative sine of x dx. Let's clean it up a little bit. And we're here. And you're thinking, oh man, gotta do integration by parts again. And maybe you're starting to think, okay, I probably chose the wrong u in dv. And maybe I did. You can try it with swapping around the u and dv, but you'll run into a similar problem. And that's all because of how e to the x doesn't change when you take its derivative or integral, and how there's this cycle with taking the derivative or integral of these trig functions. So does that mean we can't solve this integral? No, we can solve it. So if you were particularly astute, you may have noticed that this integral right here is identical to what we were trying to solve for. And if you weren't as astute, don't worry, because it's not that easy to see, and you're probably tired of this already. Like, man, I've been doing so many integrals. But yeah, this is actually a very important thing. This appears so many times, so it's helpful to be aware of. So this integral equals all of this, but this equals all of this. So let's write this integral equivalent to this, but we substitute this back in. Let's see what I mean. So the integral we were trying to solve for is e to the x sine of x dx. We said that was equal to e to the x sine of x minus the integral of e to the x cosine of x dx. But we said that this red integral was equal to this. So let's erase that integral and replace it with what we just solved for. E to the x cosine of x plus the integral of e to the x sine of x dx. So now what we can do is we can treat this integral, which is the same thing, as one massive variable and solve for it. So if it helps, let's let y equal the integral of e to the x sine of x dx. Then we have y equals e to the x sine of x minus e to the x cosine of x minus y. And now it's a simple algebra problem. Solve for y. 2y equals e to the x sine of x minus e to the x cosine of x. And that tells us that y, which is equal to the integral we were trying to solve for in the first place, is equal to 1/2 times e to the x sine of x minus e to the x cosine of x. Don't forget your plus c. And that is our answer. This last problem here is critical that you are aware of the technique that we're using to solve it, where You do integration by parts once, maybe twice, and you find the integral you were trying to solve for in your solution. In that case, just treat it as a massive variable and then solve for it like normal. This appears quite often, so it is something to be aware of, and being able to spot it will save you so much time. Because if you went back to this and tried solving that integral again, you would just be stuck in the same loop of going back and forth between these two integrals. So noticing that and being able to solve it is a very important skill to have. Anyways, this concludes our video on integration by parts, a super fun integration technique. There's so many more to learn, all of them equally or more fun than this. I guess that's debatable, but that's for you to decide. But first, you have to learn them. So tune into those videos to learn some more integration techniques. But yeah, I'll catch you in the next one. As always, take care.